So in particular, today I'm going to talk again about Lyapunov exponents, also in very different context. So today I'm going to talk about a series of results. All of them were obtained jointly with Victor Clepson from CNRS. Here it is. Here he is. And I want to start with a very simple question. So first of all, before even I talk about that simple question, when we talk about Lyapunov exponent, we usually think about the diffeomorphism that preserves a measure, and then we think about a selected theorem, and we iterate the differential of that diffeomorphism and see how the composition of those differentials grows. Or we can take an easier object. We can consider a cocycle. We have some dynamics in the base. We have some linear maps on a fiber. We can take the product of those linear maps on the fibers. Or if we can introduce a uniform system of coordinates, we can instead think about the product of matrices. Or even easier, we can just forget about the base and just talk about products of matrices formed with respect to some rule and think about the rate of growth of those products. Or, and now we reduce the question to the ones that every student should be able to answer, let's just take one matrix and multiply it by itself and see how the norm of that matrix grows. So it's well known that in this case, there is a well-defined exponential rate of growth, which is just a logarithm of the absolute value of maximal eigenvalue of this matrix. And that's exactly what we call Lyapunov exponents in this case. So let's make the situation a little bit more interesting. Let's take several matrices, or maybe infinitely many matrices distributed with respect to the same distribution, and we will choose each matrix independently and randomly with respect to that distribution. For simplicity, we can just think about two matrices, and we flip a coin and we choose one or another. And we form an infinite product of those matrices. So what can we say about the rate of growth of those matrices? Now, it turns out that, and this is a famous Furstenberg-Kesten Theorem, that exponential rate of growth is going to be defined with probability 1. And that's exactly what's called Lyapunov exponent in this case. Now, I want to say a couple of words about the very first steps in the proof of this theorem, because they will show us what that Lyapunov exponent can be represented as. So we call a sequence subadditive if it satisfies the property on the screen. So this sequence cannot be growing too fast. But it's known that in this case, the limit of n over n must exist. It could be minus infinity, it could be finite limit, but the limit must exist. This is not a complicated exercise to show that this is true. What's important is that in our case, since the norm of the product of matrices is not greater than the product of the norms, and hence if you take log of the norms, then you get a subadditive sequence. If you take the expectation, you get a subadditive sequence of non-random numbers. And since it's a subadditive sequence, we know that if you divide it by n, then the limit exists. So that limit is exactly that Lyapunov exponent that we're looking for. Of course, it's just a first step in the proof of the Furstenberg-Kesten theorem because it claims much more. It claims that you have that limit point-wise, not just on average. All right. So let's consider some examples to get an idea of what that limit could be. What could be easier than rotations? Let's just take a couple of rotations and take the composition, random composition of rotations. Well, of course, nothing happens because composition of rotations is again a rotation, and therefore the norm is going to be equal to 1. Doesn't matter how long that composition is. So Lyapunov exponent is equal to 0. Okay, of course, it's because you took rotations. Let's take one of the matrix and replace it by a hyperbolic. And let's take another one also being hyperbolic. Let's take the inverse of the previous one. If you think about that, you will see that this is roughly speaking equivalent to the random walk. And we know that when you have a random walk, then you go away from the origin after n steps by the distance, which is roughly speaking as root square of n. And therefore, roughly speaking, the norm of that matrix is expected to be 2 to the power root square of n, and therefore, when you take log n divided by n, the limit is still 0. So Lyapunov exponent in this case is also 0. Okay, that's obviously because we took a matrix and the inverse of the matrix. So let's replace one of the matrix by rotation. Let's say rotation by 90 degrees. So then you apply the hyperbolic matrix, and maybe you rotate, or maybe you apply the hyperbolic matrix again. But notice that our rotation will swap the contracting and expanding direction of the matrix A. And so if we swap those directions and apply the matrix A again, what we expanded will be contracted and vice versa. And it's not hard to see that in this case, you also have something that is very similar to the random walk, and the Lyapunov exponent is again 0. All those examples are degenerate, and the Furstenberg theorem claims that generically the rate of growth of this composition actually going to be positive. So the Furstenberg theorem claims the following. Suppose that we take the smallest closed subgroup of SL2R. So just small remark. I'm going to talk mostly about SL2R matrices. Also, all the results that I'm going to talk about holds for larger dimension of matrices. But in some cases, the conditions, non-degeneracy conditions, have to be modified. So in order to avoid the discussion, just for simplicity, I'm going to talk about SL2R matrices. In particular, Furstenberg theorem also holds for matrices of any dimension, but let's restrict ourselves to the two-dimensional case. So if the following two conditions are satisfied, so first of all, the smallest closed subgroup generated by all the matrices in the support of the distribution is not compact. And secondly, there is no finite collection of lines that is invariant under each matrix from the support of the distributions, and Lyapunov exponent is positive. But we just have seen a bunch of examples where Lyapunov exponent was 0. So let's see how it's related to these conditions. So first of all, if all the matrices are rotations, then of course it means that the support of the distribution is compact. This is not the only way to get a compact distribution. For example, you can take a bunch of rotations, and then you can take the same change of coordinates for all those rotations. You will get a bunch of elliptic matrices such that the support of the distribution, the closed subgroup is still going to be compact. So this condition eliminates the first example. In second and third example, we had horizontal and vertical directions that were invariant under each map sequence. Was there a question? No? Okay. So therefore, those conditions eliminate those examples, and Lyapunov exponent is positive. I would like to remark that it's possible to reformulate those Furstenberg conditions. So sometimes people attach some special names to them, like strong reducibility or contractibility. Anyway, it's convenient, and for us it will be special convenience since later we want to modify this condition to another case. It's convenient to reformulate this condition in the following way. If instead of matrices, we consider the action of the corresponding linear maps on the projective space, we can assume that there exists no Borel probability measure on a projective space on a circle that is invariant for all the matrices in the support of the distribution. Certainly, this, if this happens, this can be considered as a degenerate case, and one can show that in SL2R case, that's equivalent to the original Furstenberg condition. Now, if the dimension of the matrices is larger, then this is not equivalent anymore, but there are some other way to get those similar conditions. So François Ledrebier had a nice paper that studied all the possible, well, many possible conditions of this form, and so on. So I want to notice that the Furstenberg theorem can be viewed in some sense as a generalization of the strong law of large numbers, for matrices instead of random variables. So of course, you can reformulate the law-of numbers to multiplicative case. And of course, the Furstenberg condition doesn't give you such a nice explicit limit at the end. But in spirit, that's a generalization of the law of large numbers. Now, from probability theory, we know that for the law of large numbers to hold, we don't really need those random variables to be identically distributed. It's enough for them to be just independent with some other technical conditions. And here is the version of the strong law of large numbers for independent but not identically distributed random variables. So under some technical conditions, for example, if all those random variables have are distributed with respect to some measure that has a support in the same uniform compact set, then all those conditions are satisfied, then you have the same law of large numbers. So it's a natural question to ask, is it possible to generalize the Furstenberg theorem to the case when our matrices are distributed independently, but the distribution for each matrix in our product is different. So they are not identically distributed. And it turns out that it is possible. And in order to do that, in order to formalize that question, let's do the following. First of all, let's consider the family of different probability distributions. So we want all those distributions to have compact supports. I believe that this is a technical statement that can be avoided, but we assume that. And let's assume that the collection of those distributions, in a sense, compact. So what I need each of those distributions to be away from non-random, from atomic. So that's why I want them to be compact, to belong to some compact space away from atomic. And one of the simplest cases is just to consider the finite collection of probability distributions in the space of matrices. Next, I'm going to introduce some non-degeneracy conditions that is analog of the Furstenberg condition and the Furstenberg theorem. So for each linear map, we consider the induced projective transformation, and non-degeneracy conditions that we want is the following. For each of the distributions in our family, we assume that there is, you cannot find two measures on a projective space such that each matrix from the support of the distribution sends first measure to the second measure. So in the case of identical distributions, that's exactly the Furstenberg condition. There is some problem with this non-degeneracy condition. The problem is the following. If you take the distribution that is supported on just 2 points, so you just have distributions that can take your random matrix valued variable can take only 2 values, matrix A or matrix B. Then this non-degeneracy condition, unfortunately, is not satisfied. It's easy to see because what you can do, you can consider just a product of A and B inverse, and then it will be mapped from a projective space, in a sense, to the same projective space. It does have some invariant measure, and you can use that invariant measure and consider the image of that invariant measure under the linear transformation B. And you get exactly those 2 measures that we want to prohibit. There is an easy fix for that, namely, for all the proofs that we do, it's enough to assume that actually much more general, well, a little bit more general non-degeneracy condition holds. So it's enough to assume that there exists some K such that if you take a product of K matrices, then exactly that condition is satisfied. So there is no 2 measures such that it sends one to another. So if you have matrices A and B on the first step and matrices A and B on the second step, then already if you compose 2 random matrices, then you already have 4 different choices. And then most likely this condition is satisfied. All right. So if we agree that this is indeed a non-degeneracy condition, now we can formulate the result. So the result is the following. First of all, we want to fix a sequence of distributions, so just by hand. It's completely my choice. I choose first distribution for the first matrix, second distribution for the second matrix, and so on. After I fix those distributions, I choose my matrix, the first matrix randomly with respect to the first distribution, second matrix with respect to the second distribution, and so on, and form the product of those matrices exactly as in Furstenberg theorem. So what I want now, and this is what the first step in the proof of Furstenberg-Kesten theorem points to, what we should do, we should consider the expectation of the logarithm of the norm of this product. This is some non-random number, and this non-random number is kind of an average growth rate of this product. So the first theorem that shows that you have some exponential growth rate is the following. If you take lim_inf of 1 over n multiplied by this average growth rate, this is going to be positive under that non-degeneracy conditions that we introduced. When we proved that and started to talk about it, it turned out that Ilya Golshait announced this result many years ago, never published. And then we organized a small meeting in Banff and invited him, and he gave a talk and explained to us that you can give the proof of the statement in a completely different way. So currently there is his preprint already available, and there are two completely different independent proofs of this statement. But this is certainly not quite a generalization that we're looking for. So what I'm looking for is some analog of the strong law of Latch numbers. And as I said before, similar statement holds for d-dimensional matrices. So the statement that is much stronger and interesting is the following. You can consider log of the norm of the random product of matrices, and you can see how far it is from the average, which now plays the role of that Lyapunov exponent. So Lyapunov exponent is not just an exponential rate. Lyapunov exponent in this case is an infinite non-random sequence of numbers, and the claim is that we're not going to deviate from that sequence too much. So that's exactly the statement. Now, there is another statement here. If you have a Furstenberg, under the conditions of the Furstenberg theorem, we know, it was shown by Rühl, that there is a vector such that that vector, almost surely there is a vector such that that vector is going to be contracted exponentially under the action of the, under the product of the random matrices. Now, it is not true that if you just have a product, infinite product of matrices such that the norm grows, that such vector exists. Of course, for any finite product of matrices, if the norm is large, then there exists a vector that is going to be the contracting vector. But the sequence of those contracting vectors does not have to converge. In order for the sequence to converge, you need some special conditions. You need, for example, to make sure that the growth of the norm is sufficiently fast. So in this particular case, it turns out that it is sufficiently fast to make sure that such vector exists, and so we have a complete analog of the situation in the stationary case. And once again, the same statement holds for higher dimensional matrices, but I have to emphasize that non-degeneracy condition has to be improved. It has to be made stronger. The one that we introduced is not enough, is not sufficient for higher dimensional case. One can construct a counterexample. Nevertheless, generically, the same statement still holds. Okay. So I will. So first of all, I want to wave my hands a little bit about the proof. And secondly, I want to talk about the application and motivation of for this theorem. So let me start with some of the pointers towards the proof. So we're going to prove actually stronger statement. We're going to prove a large deviation estimate theorem. So we prove that we can estimate the probability that for sufficiently large n, the log of the norm of that random product deviates from this kind of sequential Lyapunov exponent in this way. And this is complete analog of the large deviation estimates from the usual probability theory for the usual random variables. And similar statement holds also for the vector. Whatever vector you take, you are going to grow exactly with the rate prescribed by this non-random sequence of numbers, and the measure of exceptions is going to be exponentially small. So obviously, if we prove large deviation estimates, then just usual parallel argument implies that we do have the result, the first result in our theorem, and the second result is a little bit trickier, but also false. So how do you do that? The idea is the following. So first of all, we're going to consider a very long product of our random matrices, and we want to cut it into the product of also long but finite pieces. We want those finite pieces to be sufficiently long so that we already feel the growth of the rate of the norm. So with very large probability, each of the pieces is going to have a very large norm. Now, if you take the log of the norm, then if we didn't have any cancellations when we take products of those pieces, then roughly speaking, we have the sum of the random variables that are independent, and large deviation estimates for this case is null. The problem is that it's kind of hard to make sure that we have that independence, because how can we guarantee that the most expanded vector of the first product is not going to coincide or to be very close to the most contracting vector of the next product? In the case of the stationary Furstenberg theorem, this was, roughly speaking, reflected in the statement that the stationary measure cannot have atoms. In our case, we have to take care of that because if there is no notion of a stationary measure anymore, so we need to do something about it. So the way to deal with that is the following. First of all, if we have any measure, we can just define some function which is just a weight of the maximal atom of that measure, and then we're going to do the following. We will start with any measure on the projective space, and then we start to choose our matrix and act on that measure by each of the matrices from our random sequence of matrices, and each time we're going to average the image. So as a result, if we start with measure which is, for example, atomic, then after the first iterate and after averaging, we can still get an atomic measure because our distribution could be atomic. We could have just two matrices, for example, and the first one will send atomic distribution to atomic distribution, and the second one as well. And you cannot exclude that the image of one atom under the first matrix and an image of another atom after the second matrix will coincide. So you cannot immediately say that each time we split the weight of the atom somehow. Nevertheless, one can prove that the maximum atom under this procedure is going to have a weight that is going to become smaller and smaller, and this limit will be equal to 0, and convergence is going to be exponential and uniform over all the choices of distributions in the space of SL2R matrices. And that is an analog of the fact that the stationary measure is going to be, for this, in the usual case, it does not have any atoms. All right. So our original motivation came from the spectral theory of Schrödinger operators. And before I go to the Anderson model, I want to say a couple of words about the main definitions that we will need. So what we're going to consider, we're going to consider an operator in a Hilbert space given by this explicit formula. So the first two terms is an analog of the Laplacian, so it's a discrete Laplacian, and V of n is a potential, and the potential is any bounded sequence. If you have any bounded sequence of real numbers in this formula, you get a bounded self-adjoint operator in the Hilbert space, and so the spectrum is going to be some compact subset of the real line. Now, how to form such a sequence? There are certainly many ways that many of them have some physical meaning. Usually people consider the following scheme. You have some measure preserving transformation, you have some observable on the phase space, and you just take a point and you measure that observable over the orbit of that point. Usually people multiply that value by some coupling constant just to see how the spectral properties behave when you change that coupling constant. So here's a picture. You pick a point, you consider the orbit, you measure the observable. That gives you some finite, some bounded sequence of numbers. You plug it into your operator. You ask what the spectral properties are. So usually people prove theorems like almost surely with respect to this measure. If you pick the initial condition with respect to this measure, you will get this and that properties of that operator. All right. So several examples. For example, if you take a potential given just by flipping the coin, potential takes values 0 or 1, depending on the outcome of your experiment with the coin. Clearly, it can be represented as ergodic Schrödinger operator by considering just a horseshoe with observable, which takes value 0 on one leg of the horseshoe and 0, 1 on another leg of the horseshoe. So this is so-called Anderson-Bernoulli potential. Anderson model is a model where you choose the potential randomly on each side and independently of each other. Almost Monsieur operator, you just take an irrational rotation of a circle and you take the potential, the observable given by some trigonometric polynomial, by cosine in this case. So 10 Martini problem claims that in this case, for any non-zero coupling constant, the spectrum is a contraset that was solved by Zhytomyrskaya and Avila, and that was one of the results that brought the Fields medal to Arthur. Fibonacci Hamiltonian, you have again a rotation of a circle with a very specific rotation number. You have an observable which is just a characteristic function of this very specific interval. The reason why we want to use very specific rotation and very specific interval is because in this case the potential can also be generated by some substitution, Fibonacci substitution, which mimic lots of properties of quasi-crystals in physics, and physicists use this model as kind of playground to test lots of properties of quasi-crystals and trying to derive those properties from the first principle, trying to solve the Schrödinger equation. Okay, so if we have this Schrödinger equation, what we can do, we can try to find an eigenvalues. Eigenvalues do not always exist. This is an infinite dimensional case, but nevertheless, if eigenvalue does exist, then we must solve this difference equation. All right. So as usually, if we deal with difference equation, we want to turn it into the properties of products of transform matrices. So if you take a vector which is just two subsequent elements of the sequence that is a solution of this equation, then one vector comes from another just by multiplying by this transform matrix. Now, it's easy to see that this transform matrix is a SL2R matrix. And therefore, in order to understand the properties of the solution of this equation, it's enough to understand the properties of the product of the matrices over the Schrödinger cocycles. So now you have the same dynamical system, but over each point in the phase space, you have a two-dimensional space, and you have a cocycle that is defined by the transform matrices. So out of the properties of the cocycle, in particular, out of the information about Lyapunov exponents, you can derive lots of properties about the spectral properties of the operator. For example, If we want just to know what the spectrum is, then Johnson's theorem claims that the energy belongs to the spectrum if and only if the corresponding Schrödinger cocycle is not uniformly hyperbolic. So uniform hyperbolicity of the cocycle is equivalent to the fact that the corresponding energy is outside of the spectrum. So what we are interested in, we're interested in Anderson model. In Anderson model, you take the discrete Schrödinger operator where the potential is given by a family, by a sequence of independent random variables that are identically distributed with respect to some given probability measure. And in this case, you can do exactly the same trick. You want to consider equation that provides eigenvalues. You want to consider transfer matrices, but in this case, the transfer matrices can be considered as random SL2R matrices, and the product of those transfer matrices can be considered as a product of random matrices. And moreover, the Furstenberg conditions for the product of this specific transfer matrices is automatically satisfied because you can see that those SL2R matrices have this very special form. And it's a relatively easy exercise to check that if you have matrices of that special form, then Furstenberg conditions are satisfied automatically. That implies that with probability 1, the Lyapunov exponent of the Schrödinger cocycle in this case is going to be strictly positive. And this is the main reason for the so-called spectral Anderson localization. So this was first obtained by Pastor Molchanov, in the continuum case. Then Consouillard proved that under the assumption that the distribution is absolutely continuous, and then in the case when the distribution is Bernoulli, that was finally done by Carmona, Klein, and Martinelli. The claim is the following. If you consider this Anderson model, if you consider the random potential defined by the family of identically distributed independent random variables, then almost surely the operator has pure point spectrum and eigenfunctions are exponentially decaying. So what happens if we take those if we take the potential that is given by random variables that are independent but not identically distributed? Notice that this setting is totally reasonable from the physical point of view, because it's completely reasonable to consider the matter where you have some background potential, say periodic potential or whatever potential, which is fixed, and then you add some random noise to that potential. So that gives you exactly this setting where you have random variables that are independent but not identically distributed. And in this case, we can still ask what are the properties of this operator with respect to almost surely. So what we can prove using this non-stationary version of the Furstenberg theorem is the following spectral Anderson, non-stationary spectral Anderson localization theorem. So suppose that the potential at each side is given with respect to its own distribution. So you have a family of chosen a priori distributions at each side, and you choose the potential with respect to the distribution. We assume that all the distributions have supports that are uniformly bounded, and we assume that variations are bounded away from zero. So roughly speaking, we assume that randomness do not degenerate. We have some non-zero randomness bounded away from zero in some sense at each side. It turns out that in this case, all the conditions are satisfied. You have that kind of sequential Lyapunov exponent well defined, and that can be used in order to prove that almost surely this operator has pure point spectrum, once again with exponentially decaying eigenfunctions. Now, interestingly enough, you don't really need to know much of the spectral theory to work on the questions like that. And in order to explain that, I want to shows a connection between the properties of the products of random matrices and spectral theory the only connections that we use. This is so-called Schnol's theorem. Schnol's theorem claims the following. If you have any bounded potential for the discrete Schrödinger operator, it does not have to be dynamically defined. It does not have to be ergodic Schrödinger operator, just any bounded potential. If we know, if we can prove somehow that any polynomially bounded solution of this equation, of this stationary Schrödinger equation, is in fact exponentially decaying, then this implies that this operator has pure point spectrum with exponentially decaying eigenfunctions. Now, the fact that our product of transform matrices with probability 1 behaves like the norm grows exponentially fast, roughly speaking, means that if you have any vector that is not growing exponentially fast, then this vector has to be decaying exponentially fast. And of course, I'm oversimplifying because this argument can be applied to a specific value of energy, but we have uncountably many continuum values of collection of energies that we want to apply simultaneously, which is certainly impossible to do. But the formal statement is the following. For any energy, it is possible that if you consider lim inf, it's possible that for some energies, the lim inf of the rate of growth is 0. But even in that case, the lim sup is going to be positive. And if lim sup is positive, it means that our solution cannot be polynomially bounded, because if it's polynomially bounded, then that non-random Lyapunov exponent would be identically would tend to 0. And this is the black box that connects the dynamical part of the proof and the spectral part of the proof. So that's where I'd like to stop. And